in a moment. Hello everyone and welcome to the National Space Academy Takeover. We're taking over the National Space Centre's social media channels all of this week to host Q&As with interesting people from the space sector. My name is Kieran and I'm the General Manager for the National Space Academy, and I'm one of the hosts for this Takeover week. Right now, I am joined by Dr. Colin Forsyth of Mullard Space Science Laboratory, who is an expert on a few different areas, and in particular, recently has been working on the impact of space weather and understanding what space weather is and how it might affect us. So, hi Colin, thanks for joining us.
Hi, nice to see you again, Kieran. Thanks for having me.
It's you've come along to events at the National Space Centre before, so this is the first time we've done a virtual meetup, but I appreciate you making the time.
No, it's you're very welcome. These are good fun things to do. I do enjoy it, and the Space Centre and the Space Academy, excellent programs to be involved in. So thank you very much for having us.
Well, thank you. And we didn't even pay you to say that. I appreciate it. Colin, could you start off by giving us a bit of an introduction into your background and the kind of work that you do?
Yeah, so I'm going to put some view graphs up so people can see. Hopefully you can all see this now.
Yep. Yeah,
so,
great.
As Kieran said, I'm Colin Forsyth. I'm from the UCL Mullard Space Science Laboratory, which is Department of Space and Climate Physics at UCL, University College London, and we're one of the largest university-based space laboratories in the UK, and one of the top space laboratories in the world. If you go up to UCL in London, oh, that's not the slide I wanted. There we go. If you go to UCL in London, this is what you will see. The UCL, the main body of UCL is sandwiched between Euston and the British Library, and we have these fantastic old buildings. But my laboratory is not actually located in the centre of London. In the 1960s, UCL got some money from the Mullard company and moved its rocketry group out of London and into the Surrey Hills. And so this, if I was in the office, which obviously I am not at the moment, this would be where I work. This is the Mullard Space Science Laboratory. It's roughly halfway between Guildford and Dorking. It's an old country house, once owned by the Guinness family, and this is where we do some of the top space science research in the world. We have a few notable features. We are the only department in UCL to have its own swimming pool, which we used to have to keep filled to have a water reserve for the fire service, because it's quite a long way to the local fire station. We build things for going into space, and we have a set of potting sheds at the back, back in this sort of area back here. Hopefully you can see my mouse. So it's the old potting sheds, which are now our machine shops, and that's where we start turning metal into the first parts of instruments that go into space. As well as those old areas, we have some new areas. We have some of the cleanest spaces in the UK because we build stuff to go up into space. So we've been building instruments at MSSL for over 50 years. We're still doing it. We provide instruments to the European Space Agency, to NASA, to the Japanese Space Agency. We've built our own spacecraft. So this image in the middle here is something called UCL Sat. It was a CubeSat that was launched about 5 year ago and was our very own spacecraft. So we built the instruments for that. That was purely a UCL thing. We're also building stuff to go to Mars, and obviously Mars is in the news at the moment with the American and the is it the Chinese and the
Arab. There's a UAE mission as well.
UAE, yeah, all landing on Mars. We have a European program which is going to land a rover in Mars, hopefully within the next couple of years. And we are building part of the camera system for that rover. And so one of the spaces that we had to develop at the lab was a space that was clean enough that we meet all of the planetary protection requirements. We're not going to send little bits and little bugs off on our instruments. This has to be incredibly clean. So we have a clean space for building all those things to send to the other planets. Now, as well as doing the building of stuff to go into space, we do the research. from those instruments. So if you want to learn about space, if you want to learn about the other planets, if you want to learn about the stars, you need to send stuff into space to do that. And then you need some people to take the information that comes back from those missions and do the scientific research on it. And that's what I do. So I take data from a variety of spacecraft that orbit around the Earth, and I'm trying to work out how the Earth interacts with the sun. And you might think that the sun just shines down on the Earth and that's the only thing that we can expect to happen. But the outer edges of the sun, all of the particles there are in a state that we call a plasma. And what this means is that the atoms out there have had the electrons stripped out of the atom. And so you end up with a positively charged ion, the negatively charged electron, and these don't come sticking back together. They're free and they move around separately and independently. And that makes their motion really complicated, because as soon as you have charged particles, you have electric fields and magnetic fields, and all these things sort of interact together. You generate both of those, they interact, and you get this really complicated movement of particles in the system. The particles in the outer edge of the sun are actually so energetic that they can escape the sun. They can escape the sun's gravity and go flying off into the solar system at around about 400 to 800 kilometers per second. So they would cross the UK in a matter of seconds, and they hit the Earth's magnetic field, squashing the magnetic field, getting captured by it, and creating this plasma environment around the Earth. And that plasma environment around the Earth feeds into things like the aurora. So we get some of that plasma escaping along the Earth's magnetic field, hitting the upper atmosphere and causing the atmosphere to glow, creating things like you can see behind me. So this is a picture that I actually got to take. Being a space scientist, we occasionally get to go and see the things that we study. And I got to go and see the aurora. And this is what we're trying to work out. How does all this stuff happen? How do these processes happen? The other thing that we want to know is, what is the potential risk from this? Because we've got loads of spacecraft in orbit around the Earth. There's something like 500 or more spacecraft orbiting at geosynchronous orbit around the Earth. So that's an orbit that goes around once per day. And it's where you put things like communication satellites or TV satellites and things like that. But when they're out in space, they're going to be bombarded by all these charged particles that are out there. And that can cause them to be damaged. And so what we want to understand is, when are these spacecraft more at risk? What are those risks? Can we predict them? We also find that these risks extend down to the ground. And so we can get things happening because the upper atmosphere is coupled by the Earth's magnetic field to all these charged particles out in space. And so we can have currents flowing between the two regions. And as these currents flow through the upper atmosphere, they can induce currents in systems on the ground. And so one of the things that we want to understand is, how and when do these currents occur? If you want to understand the basic process behind it, it's almost exactly the same as the processes that we use to charge electric toothbrushes, or if you've got a mobile phone and a pad that you put your phone on to charge it without any wires. It's exactly the same processes. It's just on a much, much larger scale. And so what we're trying to understand is, how do those processes work? When are those processes most risky to the systems that we use? We are incredibly dependent on space as a society now. Everything from GPS to data transmission to say that the power networks and the vulnerabilities that they have as well. So trying to understand that is a key part of what I'm doing. And this means that I'm involved in a number of projects. We've been developing these over a number of years in order to understand some of these risks. And we're now starting to produce tools for people like the UK Met Office, who are forecasting the risk from all of this, and something that we call space weather. How we go about this, we have numerous spacecraft flying in orbit. I mentioned there are 500 odd spacecraft at geosynchronous. Not all of them provide data for us. We normally use dedicated scientific missions, and this is just a combination of 3 of the missions that we use. On the right-hand side, we have the ESA cluster mission, something that I started using over 16 years ago when I started studying in the field, up to the Van Allen probes in the middle, and the NASA Themis mission on the left-hand side. Now, the great thing about the space science community within the sort of plasma community is that this data is freely available. These missions all cost millions, if not billions of pounds to design, build, operate. And so no individual country or no individual group can really do this on their own. And so we work collaboratively. We create these international missions, and then we put the data available online for us to work internationally as groups of scientists to study what's going on within this system. Now, my job is to take that data and to try and work out how the system works. How is the magnetosphere and this Earth's magnetic environment and plasma environment interacting with the sun as it goes through? What that means is I write computer code. I do not claim to be a computer programmer. I use a fairly simple system. It allows me to take some data in, read it in, and basically perform little bits of maths on it. But applying that to millions of data points over and over again, I can then analyze the data that we've got and come up with new understanding of the system in which we work. And one of the things I've been working on in the last few years is trying to predict something like the radiation environment around the Earth. Some of those plasma particles that I mentioned get up to really high energies, and they can penetrate into spacecraft and cause all sorts of problems. And so what we wanted to do was be able to predict when there are more of those high energy particles. And this is a year's worth of data where we did our predictions, and if it's brown or black, then our predictions were right. We were able to predict when things were going to be more hazardous to spacecraft. If it's blue or pink, then we didn't do quite so well. And actually, you can see that this is pretty good. It's mostly brown and it's mostly black. So we're able to develop these forecasts for when satellites might be at risk. The other thing I get to do, being part of a space lab that builds things, is be involved in the next generation of spacecraft. This is one that we were involved in and launched last year, just over a year ago, in fact. This is ESA's Solar Orbiter mission. The lab that I work at is involved in 2 of the instruments on board here. One of the ones which is going to image the sun, and then this little one that you can see out the back looks like 2 circles. This is our electron detector. So we're actually detecting the electrons flying off the sun. The professor in charge of this calls this the spacecraft's nose. It sniffs the solar wind as it comes flying past. So this has just launched. We're starting to get really exciting data coming from that, but we're also thinking about what comes next. And the next mission that we've got coming along, still in the development phase, is something called SMILE, the Solar Wind Magnetosphere Ionosphere Link Explorer. And this is a fascinating mission which is going to allow us to see the unseeable. Most of Earth's space environment, we can't see the processes going on. But what this is going to do is actually see X-rays that come off of some of that interaction between the sun and the Earth, and allow us to see the outer edge of our space environment, which is going to be absolutely fantastic. It's a really exciting mission that we've got coming up, hoping that that will go to launch in 2024 and be giving us new science data from then. So yeah, that's a little bit about me and what I do and the work that we do at the Mullard Space Science Laboratory.
Brilliant, thank you, Colin. I've got to say, I always love how it's not just space scientists, but whenever space scientists do it with big missions, and a lot of other researchers do it with other projects, when you have an acronym and you get a name like SMILE for a spacecraft that's going to see, you said see in X-rays it's going to see?
Yeah, we're going to look in soft X-rays at the edge of the magnetosphere.
And so this is a really high technology piece of, high spec piece of technology. It's going to see things that we can't see with the human eye. And we've given it the name SMILE, which is kind of name, but there's great acronyms out there. I'm always impressed with telescopes being called things like Very Large Telescope and really basic acronyms.
Sometimes the basic ones work, but sometimes it's fun to come up with something a little bit more exciting as well. So we have SMILE, and one of the other instruments that I used quite a lot was called PEACE, PEACE. So,
do you remember what it stands for?
The Plasma, Electron and Currents Experiment.
Oh, well done. So I think you did a really good job in your description of explaining what a plasma is. And I think for a lot of people who maybe aren't into science, understanding that we've got particles streaming from the sun is quite hard to get your head around. But you mentioned about the aurora as the aurorae as one way, and we can see your picture a little bit more clearly now that we're not seeing your slides. So just tell us again where you saw that aurora in your picture.
So this was taken in Tromsø in northern Norway. So one of the perks of the job that I do is that since we study these things, we do get the chance on occasion to actually go out and see them in real life. And I came back awe-inspired, and seeing the light above your head filling the sky is absolutely phenomenal. And you understand then where some of the sort of the myths and why people really relate to this sort of thing, where that all comes from when you can see it in that way. And it just gives you that added impetus to go back and go, right, let's understand that a bit better. What's going on here? Because it's a complex thing. I mean, this is a relatively simple aurora. And I've been working with groups of people, and actually, although we sort of understand the basics behind where the aurora comes from, being able to explain this versus when it curls up versus when it's patchy or pulsating or incredibly dynamic is a really complex thing. But the physics is all there. We understand the physics. It's incredibly basic physics in some senses, but it comes together in these complex ways. And understanding the system from that is challenging, but it's also fun.
I think Aurora is very beautiful. I was very lucky to see one in Iceland a few years ago, and it was one that spiraled and had red colors in it, which is, I didn't know that could be a thing. And to think about, yes, the physics of that, those are the charged particles hitting the atmosphere, and they're coming, correct me if I'm wrong, I'm trying to kind of put this out for lay people. They're coming along because that's where the magnetic field is directing them. And that's why you see them near the North Pole. And sometimes you can, I think, see them in the north of the UK, but it's very, very rare that they spread that far. Is that right?
You can. So Earth's magnetic field expands out into space and creates this region that we call a magnetosphere. Now, if everything was nice and simple and there was nothing else going on, then the magnetic field would effectively seal us off from everything else in space around us. However, that's not the case, because our magnetic field can link up with a magnetic field which is also being dragged off of the sun along with all those particles. So those particles come flying off the sun, drag a little bit of the sun's magnetic field with them, and that can link up with our magnetic field. And when it does that, it suddenly opens up this system and allows us to capture some of that plasma that's streaming off the sun, and it gets held on our magnetic field lines. But there's this boundary between those magnetic field lines which are sort of linked ultimately to the sun or out into space, and those magnetic field lines that loop around the Earth and just come back and come back in on the other side. And at that boundary is where we see the aurora. So we start to see the aurora around about that bit. Now, that boundary and where that is dependent on how much of Earth's magnetic field is opened up. And that can change with time, and actually it can change with some of the things that come off the sun. So we have this, if we want to talk about this in terms of weather, we have this sort of steady wind and drizzle that comes off of the sun towards the Earth, and that's every day, and there's things that happen around that. On occasions, you get these ejections from the sun. We call them coronal mass ejections, where you get a bunch of solar magnetic field and particles, and it flies off the sun at around about thousands of kilometers per second. So it's actually traveling faster than everything else. And when that hits the Earth, it drives the system that we have. It opens up more of our magnetic field and forces the aurora down to lower and lower latitudes. And that's when we see it in the UK. And when you get one of these coronal mass ejections, if it has all the right properties, it can force the aurora down to those low latitudes. And if you're in Scotland, you're more likely to see it. If it's a really big event, then it can push down. And it was around about 7 years ago, we actually had the aurora being reported as being seen from Guildford.
Wow.
Yeah, enormously low latitudes. But that's very rare. We maybe see that once every 11 years if we're lucky.
And I guess that's what you're trying to understand is, we know that this material is coming off of the sun. You've just described how that changes. And in your slides a moment ago, you talked about how that potentially could have an impact, because it is charged particles in magnetic fields, that could have an impact on the electronics that we rely on in space, so the satellites that we rely on. And then you also talked about the potential for it to risk the electronics on the Earth.
Yeah.
And so how worried should we be about space weather?
Well, that's a difficult question, in that these are, the big events, the really damaging events are rare. And we have certain amounts of resilience built into our systems already. We have seen times when these events have impacted on the ground. The famous two that we refer back to are called the Carrington event from the 1850s, which is largely before most of the technology that we use today was around. Probably one of the most advanced pieces of technology was the telegraph. But we saw effects on that. There are reports of the telegraph system being damaged because the currents flowing through the lines were so great and caused all sorts of problems there. In 1989, we saw a problem in the power network in Quebec, where the currents that were generated actually damaged one of the transformers on the power system. And we're not talking about the little transformers that we all use every day in our electronics. We're talking one of the big ones attached to the generators. So there are times when it's happened, but it's still relatively localized, and we have resilience within that. What we're trying to work out is what the worst case scenarios might be, and then try and be ready for that. So we as the scientists work with government agencies, with power providers, and try and explain to them what we think the scenarios will be, how bad the fluctuations in their network might be, and when those might happen. It is then down to them to sort of come up with the plans as to how they work. And it's a tough thing to be able to do, because we're trying to predict these things, and we're getting better at predicting them, but we're not always going to get it right. We've got not many events to fall back on in history to build our forecasts from. And you've got to judge how you react to a potential forecast of some risk versus, do you turn the power off, or do you turn your service off for a length of time and make your customers quite unhappy?
And how do you predict that it's going to happen as well? When would you decide to cut service or something like that?
Yeah. And that's, let's say that's quite a challenging thing to do. We know the conditions in the solar wind somewhere between an hour and 20 minutes before it actually arrives. We have spacecraft which are at a point that balances Earth's gravity and Sun's gravity. It's called a Lagrange point, and it sits about 200 million kilometers upstream of the Earth in the solar wind. And we can see stuff flowing past spacecraft that are there. And by working out how fast it's going, we can work out roughly how long it will take to get us.
It
And
sounds like it's ripe for a disaster movie, Colin. I wonder if you might end up working on something like that one day. You get this alert, what, an hour and 8 minutes, did you say, ahead?
well, it's somewhere between 20 minutes and an hour.
Okay. And you get the alert that this is something, I can see that being a disaster movie.
Well, I think it was, there was something on Sky last year, I believe, where they talked about a space weather event and looked at the consequences of that going forward. Yeah, you do see it popping up in various bits of science fiction and so on as to what these impacts might be.
It's also why it's so important for scientists like yourself to be able to explain things to, we're talking about to hopefully a young audience today through this video, but if you have to explain things to politicians and government advisors, yesterday's evening Q&A, we spoke to Anuradha Damale, Damale, I said her surname wrong twice now, about she's hoping to build a career in space policy, and it's all about that communication and making sure that the risk is understood, because it's quite hard, like you say, you're building these models, and I guess over time you'll build better models and be able to give like more concrete advice.
That's the idea, and that's where the programs that we've been running, like so I mentioned 3 of them on my slides: RADSAT, SAT-RISK, SWIGS. We have another one called SAGE, and these are all at least 2 of those are being under an umbrella called SWIMMER. You were after the acronyms from earlier. We can come up with interesting acronyms. But the idea is to take the science that we've been doing over the last couple of decades and make the best forecasting tools that we can, and bring the forecasting as close to up to date as we can. Because then we're in a position to use those forecasts and say, right, this is what the forecast says. It's then down to the next line to say, right, what are we going to do with that information? And part of that is understanding the limitations of those forecasts, but part of that is saying, well, maybe if it is saying that something bad is going to happen, we need to know. We actually, every one of us does it just about every day with the weather forecast. We have the weather forecast and it says there's a 40% chance of rain or a 60% chance of rain, and you sit there and you think, well, do I take my umbrella or not? It's the same sort of idea, but just applied to a service provider, a service network, where they think, well, what do we have to do with that forecast information?
So the application of your research then is really clear to how it could impact the services that we use from space and life on Earth. But I wonder if there are any big mysteries around the sun, the particles that are coming from the sun, the Earth-Sun interaction. Are there any big mysteries that you're interested in just because you're curious about them? Like if there was one thing that you would hope to solve or see solved, what would you like to know?
Well, the one thing that I'm really interested in is actually a smaller event. It feeds into the bigger events, but it's called a substorm. And these substorms are basically what gives us most of the aurora and things like that. We know roughly what causes them. We know roughly the sort of conditions that we can expect them to appear in, but we've been arguing about what the physics behind them is almost as long as we've known about them. We've known about them for the last 50 years, and we still can't decide on what the fundamental driving physics of these events that give us bright aurora across the sky are. We've got all these ideas, and what we'd like to do, or what I'd like to do, is pin that down. What is the thing that causes the aurora from these substorms? And is it one thing? Because we've got all these ideas. I mean, we've got this complex system, and we've sort of labeled all the times that the aurora can get really bright across the night sky and give us all sorts of other effects. We call them all substorms. And we sort of have this idea in the back of our minds that it's the same thing that causes them. A leads to B, leads to C, leads to aurora. But is it? Or is it that A leads to B, but sometimes C can happen beforehand because of something else? And it's a more complex thing. Does everything need to lead one into the other? Or is it conditions that we need to care about? And how do we test that? So one of the things that I'm thinking about now is can we look at the times when things are really, really quiet and then go nuts? Because that's the sort of extreme of the system. And if you look at the extremes, maybe we can get a better idea about the things that happen more regularly.
And in between. And it's such a complicated system. And I know that physicists, when you study physics, there's a tendency to kind of, as you learn, to reduce systems to really simple models, and then you get that more complicated modeling. Well, I hope that you do manage to get into that mystery. It sounds like a great mystery.
It is, it's a fantastic one.
We're kind of coming to the end of our time, Colin. So I just wanted to, I've been asking everyone this. So you're working as, you know, in physics now, and in particular, I guess, solar physics. If someone wanted to work in your area, if someone's been interested looking at your Aurora picture and going, I want to know how that works too, or to work in a similar area, what would your advice for a young person be?
So the typical pathway into this sort of research and this sort of study is a very academic route. It's GCSEs into A levels, into a degree, into a doctorate, into hopefully a job within the industry. In terms of how you would go about that, I always come back to maths being an incredibly important thing. Physics is essentially applied maths. It's maths with some rules, and if you can understand how maths work, if you can get into that way of thinking about how you do things. I mean, I said earlier, all that I'm doing in most days when I'm doing my computer programming is having a bit of maths and then just pushing lots of data through that bit of maths to get my answers out. So it's a very mathematical thing to be able to do that. Just be interested as well. You know, find something that's interesting to you and follow that. And don't be surprised if some of the things that you're interested in early on, you don't necessarily follow that through all the way through. I was when I was younger, I was interested in astronomy and the stars and the planets and all of that sort of thing. As I went through my my school life, my university life, I learned about plasmas and the aurora, and my course was diverted. And this is where I've ended up. I study something which I find absolutely fascinating.
Yeah.
If people aren't necessarily mathematical in their mindset, or don't want to go down the physics or studying route, then we have people building stuff, and we need people to build stuff. You know, getting hands-on with bits of metal or bits of electronics, you know, designing some of the underlying code for some of these instruments. You know, these are things where there's almost an alternative route into this. You can be involved in it. You might not be doing the research and taking the data coming down, but you're an incredibly important part of the process by creating that data in the first place. We can't do what we do as scientists without that initial data, and that means having people who build spacecraft, who build instruments, who organize all of that. You know, the people that come together, and I have enormous respect for the project managers who can juggle all these different things that are going on and get us to something phenomenal that works and gets launched into space and provides all that data back. So there's all sorts of different routes into a career in the space sciences that aren't necessarily being a scientist. And all of them are really, really important.
It's a collective effort then to create a craft, send it out there, and then get that data back.
Yeah.
That's brilliant. Thank you so much, Colin. And I'm just going to stick in here that I find something like the Aurora can be beautiful, but when you understand that there's a way we can understand it more deeply from the maths and the physics, that it makes it even more beautiful in my eyes. I know not everyone, some people would maybe just want to see it visually, but I think it's a good point about maths being a great way into the sciences. And in terms of building spacecraft, we have tomorrow's evening Q&A. We've got an apprentice from Oxford Space Systems who builds spacecraft, going to talk to us about being a space apprentice, which is, I think, quite a unique pathway into the sector. So I thought I'd just mention that in there. Colin, thanks so much. We'd love to have you come to Space Centre again, National Space Centre, when it's open again. enjoy your models and your maths and your aurorae, especially if you get to go to Norway again.
Thank you very much, Kieran. I look forward to coming back when we return to some form of normality.
Fingers crossed. We've got enough to worry about without the sun throwing stuff at us. You're looking after that, so I feel we'll be okay. To those of you watching, remember you can see more of these Q&As all week here at the National Space Centre's YouTube channel. You can get in touch with the National Space Academy on Twitter, which is @UK Space Academy. You can go to our website, nationalspaceacademy.org, where you can find a form to contact us. If you send us your space careers questions, we may be able to put them to our other guests later in the week. Thanks again to Colin, and thanks to everyone who was watching, and we'll see you again soon.